All right, this video is going over pages 13 through 15. So we're going to start by talking about the Doppler effect. So if you stand at a railway crossing as the train approaches with its horn blowing, the pitch, which is your perceived frequency, so remember frequency determines pitch, that you hear will be higher as the train moves closer to you. And once it passes you, that pitch is going to get lower. So the pitch gets higher, okay, when it comes towards you and gets lower as it moves away. That is a perceived difference in frequency due to the motion of the sound or the source. So that's called the Doppler effect. Okay, so the way we're going to basically kind of do an example for this is we're going to have a bug bobbing up and down on a pond. So figure 1 is where the bug is just sitting in place, okay, just bobbing up and down, creating waves. Okay, figure 2 is bug is now moving to the right. Okay, so it's still bobbing the same frequency, so we didn't change anything like that, but now we just added movement to it. So number 1, how will the frequency of the waves reaching an observer at A compared to the frequency of waves reaching an observer at B? So in figure 1, if you notice, frequency is the number of waves. Does A or B look any different compared to each other? And let's just pretend this is sound. Let's pretend these waves are sound. Would there be any difference in frequency between A and B? No, there would not. Okay, so it would be the same. Okay, because your source, or in this case the bug, is not moving. Okay, so there's no difference in frequency. Okay, no difference in wavelength there. So number 2, how will the frequency of the waves reaching observer C compared to the frequency of the waves reaching observer at D? So what happens is in the Doppler effect, pretend this is a sound wave, is when you start moving in this direction, what happens is these waves start to bunch up in front of the bug, and it starts to create a higher frequency because those wavelengths are getting shorter. And then once it breaks through, so all the waves behind it are getting further and further apart. Okay, so that's why at part D you would have a very high pitch because your frequency goes up. And on C, you'd have a very low pitch because the frequency is lower. Okay, so in this case, frequency at D is greater than frequency at C. Okay, is the bug actually bobbing up and down with a different frequency in figure 1 versus figure 2? Nope, so remember we didn't change the bug's original frequency, so no. Original frequency does not change. Okay, so again, bug still bobs the same, but when you start adding movement to it, now that's going to start compressing waves and stretching them out based on which direction it's moving. So what is causing the perceived change in frequency from figure 1 to figure 2? Okay, it is all relative to the motion. So relative to the motion of the bug. That is relative to the observer. Okay, so that basically means is D is going to perceive a different pitch than C because its position is different relative to the bug, and then it's also determined by the motion of the bug in relation to the observers. Okay, so that is your Doppler effect. So that bunching of waves is kind of like what we're about to talk about in the next part, is Mach. Okay, so anytime you are traveling below the speed of sound, that's called subsonic speeds. Okay, so when the speed of an object equals the speed of sound in that air temperature, that's called Mach 1. Okay, so if you're traveling at Mach 1, that means you are traveling at the speed of sound at that particular temperature and that location. So let's just say if my speed of sound was 332 meters per second, okay, that would be Mach 1. So Mach 2 would be 2 times that. So that would be going 664 meters per second. So speeds that are greater than Mach 1 are called supersonic. Okay, so planes can achieve this now, so we've definitely broken sound barriers before, so I'd make sure you know your terms here. Okay, subsonic speed, what is Mach? Okay, supersonic speed. Now going more into Mach, Mach is, if you want to calculate your Mach number, okay, or how fast you're going, okay, it is simply the speed of the object divided by the speed of sound. Okay, so there's no units for Mach. It's basically a ratio. So if you're traveling at 1.5 Mach, now you don't even have to say Mach, but it makes it if I add Mach to it, you know I'm talking about the speed of sound. So if I'm traveling at 1.5 Mach, Mach isn't in units, it's just basically so you know that I'm talking about sound. Okay, it just means you're going 1.5 times the speed of sound. So we're going to do some calculations here. So speed of sound at sea level and 0 degrees Celsius is 332 meters per second, or approximately 1,200 kilometers per hour. Okay, so this is something, remember that equation we give you, V equals 331.5 plus 0.6 times t. Well, if you put 0 at t, okay, that whole thing goes to 0, which basically means your velocity be 332 meters per second. So that's where that's coming from. And if you wanted to convert that to kilometers per hour, so if you want to go from kilometers per hour to meters per second, okay, you would divide by 3.6. And if you want to go from meters per second to kilometers per hour, you would multiply by 3.6. So that's where they get that 1,200 kilometers per hour from. So number one was the Mach number of an aircraft traveling at sea level and 0 degrees Celsius with a speed of 1,440 kilometers per hour. So all you gotta do is take 1,440 and divide that by your 1,200. Okay, put that in the calculator, and you should get a value of 1.2. So that is your answer right there. There's no units for it. That just means you're going 1.2 times the speed of sound. And this would be considered, if I asked, it would be considered supersonic. Anything above Mach 1, okay, or 1 is supersonic. Anything below would be subsonic. So in this next part, 920, so 920 divided by 1,200, that gives me 0.77. Okay, so this would be below Mach 1, so it's not traveling as fast as the speed of sound, so this would be called subsonic. Now, a military interceptor plane can fly at Mach 2. What is the speed in kilometers per hour at sea level and at 0 degrees Celsius? So at Mach 1, okay, we know that it is about 1,200 kilometers per hour. So Mach 2, all you gotta do is 2 times 1,200. That means the plane is going about 2,400 kilometers per hour. 3, what is the Mach number of a plane traveling at each of the following speeds at sea level? Okay, so we're not going to change sea level. We're not going to change height on you at all, so it's all going to be sea level. But now if you notice, I have a temperature here. Okay, so you can no longer go back to that whole 332 thing. Okay, so my velocity is going to be 331.5 plus 0.6 times 12. Okay, and that's going to give us a velocity of 338.7 meters per second. So that is our speed of sound at that temperature. So that is Mach 1. So at 1020, so 1020 divided by 338.7, that means I'm going about Mach of 3.1. So that would be considered supersonic. Okay, 170 meters per second, so 170 divided by 338.7, and that gives me 0.5 Mach. Okay, so that would be subsonic. Now C, watch out for things like this, is if you notice I'm in kilometers per hour, and my speed of sound that I solve for is in meters per second. So I'm gonna do is I'm gonna divide this by 3.6 to get it back to meters per second. And that's gonna give you about 510 meters per second. So now I can do it, so 510 divided by 338.7, and that gives me a Mach of 1.5. And that'll end that one.